All right, in 3.4, we are going to take a look at zeros of polynomials. So the first idea that we're going to look at is the rational zeros theorem. This is going to allow us to make a list of all of the possible rational zeros. And remember, a rational number is just something that can be written as a fraction. So the way that we find all possible rational zeros of a polynomial is we take all of the factors of the constant and put those over all of the factors of the leading coefficient. Okay, so in this first example polynomial, we're saying that we want to take all of the factors of 3 and put that over all of the factors of q, right? Or over all the factors of 2. So the way that we're going to write that out to start, we're going to put plus or minus. We need to include the positive and negative factors of the constant. So the constant is just 3. The only factors of 3 are 1 and 3. So I'm going to write those as plus or minus 1 and plus or minus 3. And then those are going to be over all of the factors of 2, which are just 1 and 2. So since I'm including the plus or minus in the numerator, I do not need to include it in the denominator. But now what we want to do is actually split this up into numbers. So I'm going to list first the plus or minus 1 over 1 and plus or minus 1 over 2. Actually, let's do it this way. Plus or minus 1 over 1 and plus or minus 3 over 1. And then we'll do plus or minus 1 over 2 and plus or minus 3 over 2. Okay, so we come up with this list right here of 8 possibilities, right? Positive 1, negative 1, positive 3, negative 3, positive 1/2, negative 1/2, and positive 3/2, negative 3/2. This list is all of the possible rational zeros. Now, there may not be a rational zero. It is possible that we would not have a rational zero. But if there is at least one rational zero, it has to come from this list. So now the next step to actually finding these rational zeros is to start testing these numbers using synthetic division. Generally, we start with the lowest positive possible rational zero. So in that case, that would be 1. And we're essentially just guessing and checking, right? I have no idea if 1 is actually going to be a root or not. I'm just going to start taking numbers from my list here and checking to see if they are zeros. So I'm going to list out my coefficients of my polynomial, and we will synthetically divide. So bring that 2 straight down, multiply 1 times 2, add, multiply, add, multiply, and add. Since I get 0 here, that means there is a 0 remainder, and 1 is a 0. My depressed polynomial here then, since I started with a cubic, this would be a quadratic. So this will be 2x squared plus 7x plus 3. And now I just want to solve this. So I'm going to set this equal to 0, okay, and solve this quadratic. Now, it's always worth it to see if we can factor, right? Because factoring is usually quicker than using the quadratic formula, but you can always use the quadratic formula. If you don't want to bother with factoring, you can just jump right into the quadratic formula. But I'm going to factor this one. So to x factor, we need to multiply a times c. So 2 times 3 is 6. Then my b term is 7. So I'm looking for 2 numbers that multiply to 6 that add to 7. Well, I think that would be 1 and 6. So I could split this up into 2x squared plus 1x plus 6x plus 3. Remember, if my leading coefficient on the quadratic is not 1, I have to factor by grouping at this step. So I will group the first two terms, group the second two terms. I can take an x out of this, so I'd be left with 2x plus 1. And I can take a 3 out of here, so I'd be left with 2x plus 1. So this would factor into 2x plus 1 times x plus 3. And if I set each of those equal to 0, subtract 1, divide by 2, I would get x equals 1/2. Here, I would just subtract 3, and I would get x equals 3. So I end up with 3 answers, okay? The first one was 1, and then I also got 1/2 and 3. Okay? Those are all of the zeros of my polynomial. All right? Let's take a look at another example here. Now this one says we want to solve 3x cubed minus 8x squared minus 8x plus 8 with the help of a graphing calculator. So we still want to list out all of our possible rational zeros first. Okay? To do that, we want to take all of the factors of the constant. So all the factors of 8 would be 1. So we could do 1 and 8 and 2 and 4. Right? So I'm going to list that out like this. And then over all the factors of my leading coefficient, which is just 3. So, oops, don't need my plus or minus down there. So just over 1 and 3. So to list all those out then, we'll have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 8 over 1. And then putting all of those over 3, we'll have plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 4 over 3, and plus or minus 8 over 3. So we have quite a few possibilities for this one. All right. Now, when it says with the help of a graphing calculator, what we want to do is plug that function into y equals and look at the graph. Okay. Now, if I look at the possible places or the places where this graph crosses the x-axis, and it looks like I've got one value that's a little greater than 3, but on my list, there is no possible rational zero that is greater than 3, right? Or that is in between 3 and 4, I should say. We could then look at these two possibilities. This one, a zero in between 0 and 1, looks like that could be 1/3 or 2/3, probably closer to 2/3. And then we also have a zero that's in between -1 and -2. So that could potentially be -4/3. So we've got two possibilities to check looking at the graph, right? Maybe -4/3, maybe 2/3. What we know about this one, though, since there is no rational zero in between 3 and 4 on my list, this is going to have to be an irrational zero. Right? So let's start by checking 2/3. Okay, let's see if that works. So I'll put 2/3 in my box, list out my coefficients, and synthetically divide. So bring the 3 straight down, multiply 2/3 times 3 would be 2, add, multiply, add, multiply, and we get a remainder of 0. So 2/3 is one of my zeros. Now I'm going to take my depressed polynomial and solve. So like we said, it's usually worth checking to see if it factors. So a times c would be -36, b is -6. So two numbers that multiply to -36 that add to -6. I don't think that exists. I think in this case we're going to have to use the quadratic formula. So x equals the opposite of b would be +6 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And then we'll just simplify. So 6 plus or minus 36, and then 4 times 3 times 12 would be 144. So plus 144, right? Because we've got a double negative there. And that's all over 6. So 6 plus or minus the square root of 180 over 6. Now I think we can simplify this. I think we could write this as the square root of 36 times the square root of 5, and then the square root of 36 is just 6. So the square root of 180 would simplify to 6 radical 5. And then I can actually split this up and make it 6 over 6 plus or minus 6 radical 5 over 6. And the 6's would just reduce, and this would become 1 plus or minus the square root of 5. So again, we end up with 3 answers, right? My 3 zeros are 1 minus the square root of 5, 2/3, and 1 plus the square root of 5. Okay, and I just wrote those in chronological order. All right, now with this example, this is a good place to mention the conjugate pairs theorem. If we have a polynomial with an irrational zero, then its conjugate also has to be a zero. So in this example, we found that 1 plus the square root of 5 was a zero. 1 minus the square root of 5 also has to be a zero. Another example was if 3 plus the square root of 2 is a zero, then 3 minus the square root of 2 is a zero as well. All right. Now, next, we're going to talk about Descartes' rule of signs. But first, let me give you a little history lesson on Rene Descartes, because he is one of the most important mathematicians for our purposes. Okay, so Descartes was born in 1596 in France, passed away in 1650 in Sweden. He was a geometer, algebraist, but actually was known more for philosophy. He's known as the father of philosophy. He was born in La Haye, France, but that is actually now known as Descartes, France. He was that important that they named his hometown after him. He graduated from college with a law degree, actually, but that didn't actually interest him. He was much more interested in philosophy and questioning things in his life. He questioned anything that could not be derived logically, and even questioned his own existence, and is credited with the very famous "I think, therefore I am." He was really the first to use what we call analytic geometry. He used algebra to investigate geometric relationships. Um, he created the Cartesian plane, the XY coordinate plane. He was the first to really start plotting points and using pictures like that to express or to show algebraic equations on a graph. Cartesian is just a Latin form of his name, and so the Cartesian or coordinate plane is named after Rene Descartes. He also standardized the use of variables. He was really the first to use x, y, and z for unknowns in equations, and then a, b, and c for knowns. And he also created our standard notation for superscripts, like how we write x to the 4th power. He was the first one to do that and standardize that notation. Now, what we're actually going to use of his in this section is called Descartes' rule of signs. So let's take a look at that. So Descartes' rule of signs just says, well, first, let's talk about what a variation in signs is. A variation in signs occurs when the signs of two consecutive terms differ when the polynomial is in descending order of power. So we have to make sure that it's in standard form first. Then I would look at the change in sign. So for this example right here, my first term is positive, my second term is negative, my third term is negative, my fourth term is positive, and my fifth term is positive. So what we're looking at is anytime we change sign, that occurs right here and right here. So this example would have two sign changes. Okay, so now let's look at what that means for our purposes. Right? Descartes' rule of signs just says that the number of positive zeros of f is equal to the number of variations of sign on our function, or is less than that by an even integer. So in our example there, since we found two sign changes, we would say, well, this polynomial either has two positive roots or zero. Okay, we would subtract an even amount from that. Then the number of negative zeros is equal to the number of variations of sign of f of negative x. So if I were to plug negative x into the function, right, or is less than that by an even integer. So let's do this example here. All right, on my f of x, my first term is positive, my second term is positive, my third term is positive, my fourth term is negative. There is only one sign change. That means that there is one positive zero. Now to find negative zeros, or to find how many there would be, we plug negative x into the function. So I'll have 2 times negative x to the fifth plus 3 times negative x squared plus 5 times negative x minus 1. And that would simplify to, so this would become negative, right? Whenever we have an odd power, that would be negative. So negative 2x to the fifth. Whenever we have an even power, that would stay positive. So plus 3x squared minus 5x minus 1. So we've got negative, positive, negative, negative. That's two sign changes. What that means is we have either 2 or 0 negative zeros. Okay? It's always that number of sign changes or less than that by an even integer. Okay? Our last idea is bounds on our real zeros. Okay, so when we have our big list of possible rational zeros, okay, and we start testing them to see what works, we could find upper bounds or lower bounds. Okay, so an upper bound means there are no zeros greater than that number. A lower bound means there are no zeros less than that number. So our rule for bounds is if we do our synthetic division and in the last row every term is 0 or positive, then that k, that number that we plugged in, is an upper bound. There are no zeros greater than that. If we have a negative number and in the last row the signs alternate, then k is a lower bound. Okay, so let's find the upper and lower bounds on this polynomial. Okay, now first we would want to list out our possible rational zeros. So we take all the factors of the constant over all of the factors of the leading coefficient. So all the factors of 6 would just be 1 and 6 and 2 and 3, right? And in this case, we are just putting those all over 1 because my leading coefficient here is 1. So normally we would start by plugging 1 in and testing to see what happens. But for time's sake here, I'm going to jump all the way up to 3, right? If we plug in 1, we would see that it is not a 0 and it's not an upper bound. If we would plug in 2, we would see it's not a 0 and not an upper bound. So I'm going to plug in 3 here. So if I list out my coefficients, I'll have 1, -1, -5, -1, and -6. So synthetically divide, bring the 1 down, multiply, add, multiply, add, multiply, add, multiply, and add. Now, 3 is a 0, but if we look at this last row, every term is positive or 0. That's what this is saying. If everything is 0 or positive, then k is an upper bound. Right? So this means that there is no 0 greater than 3. I can immediately discard 6 off of my list. Okay? Now, we can then start testing negative zeros. Okay, so normally we would start by testing -1. We would find that it is not a 0 and it's not an upper bound, or I'm sorry, not a lower bound. So just for time's sake, for this example, I'm going to go ahead and plug in -2 then. So again, I'm going to use my coefficients here of 1, -1, -5, -1, and -6. So bring the 1 down, multiply, add, multiply, add, multiply, add, multiply, and add. So we actually find that -2 is a 0, but we also find in the last row here that since I'm alternating signs every time, positive, negative, that means that -2 is a lower bound. That means that no zeros are less than -2. I can immediately discard -3 and -6 off of my list. Okay, now note, zeros in the last row can be regarded as positive or negative. So if I would have gotten a 0 here, for example, we could think of that as negative. All right. So that is it for this video. The final question is going to pop up asking you what questions you have.